So, let's talk more about pH and pOH of strong acids and strong bases, but this time let's talk about it in regards to reactions between the two. For instance, here we're asked a question about the volume of HCl, hydrochloric acid, that we need to completely neutralize 25 milliliters of sodium hydroxide. Now what we should first do is write a reaction that we're describing, and of course we're taking hydrochloric acid, an acid, and we're reacting it with sodium hydroxide, a base. And of course what happens here is the hydroxide ions react with the protons from the strong acid and the strong base, and they form water, and the remaining product would be aqueous ions of sodium and chloride. Now, this is the total molecular reaction and how it would be written with phases. This would be aqueous, this would be aqueous, this would be liquid water, and this would be aqueous. But we often like to write what are called net ionic equations, and what's really going on here is the sodium and the chloride aren't reacting. The protons from the strong acid are reacting with the hydroxide ions from the strong base, and the net result is water. It really doesn't matter how you write your strong acid, strong base reaction. They're all 1:1:1 stoichiometric ratios. 1 mole of this acid reacts with 1 mole of this base, and the product is 1 mole of water and 1 mole of sodium chloride. Or 1 mole of protons from the acid neutralizes 1 mole of hydroxide from the base, and you get a mole of water. So we're asked what volume of HCl, and we're given a molarity, 2.00 moles HCl per liter solution. What volume of this solution is needed to complete the reaction, to completely neutralize this volume of this molarity of sodium hydroxide? And this is stoichiometry. We were asking how much of this do we need to react all of that, so that none of either is left over. There's no limiting reagent. Both reactants, in a sense, are limiting. They both get consumed completely. And since we're doing stoichiometry, we like to work with moles. So, of course, the first thing I'd say is, well, if I have a volume and a molarity, I essentially have moles of the sodium hydroxide. 1.30 moles sodium hydroxide exist in every liter of that solution. And in this case, we're using 25 milliliters. In liters, that's 0.0250 liters of solution. In other words, what we're using is 0.0325 moles sodium hydroxide are being consumed in this reaction. And of course, if we're doing stoichiometry and it's a 1:1 ratio, I can actually erase this amount and continue doing the problem, because stoichiometry allows me to use the coefficients in a balanced chemical equation, implied ones, to convert from moles of one reactant to moles of the other. And so in this case, for 1 mole of sodium hydroxide, we will need to use 1 mole of HCl. So what I've done here is, by using the number of moles of sodium hydroxide I had to neutralize, I have figured out how many moles of acid it's going to take to neutralize that sodium hydroxide. And the question says, what volume do you need? And that's not a problem, because I know the molarity of the acid solution, and molarities let me convert from moles to volumes, or volumes to moles. So all I do is use that molarity right now. Namely, there are 2 moles of HCl in every liter of that solution. And this gives me the volume needed to neutralize all this sodium hydroxide. And the value comes out to 0.0163 liters, otherwise known as 16.3 milliliters of solution. So you see, it's going to take me 16 milliliters of this more concentrated solution to neutralize 25 milliliters of this less concentrated solution. And that makes sense because I need the two reactants in a 1-to-1 ratio. Let's look at a further example. In this problem, I'm asking it the other way. If 30 milliliters of 0.5 molar NaOH completely neutralize 40 milliliters of nitric acid, what is the molarity of the nitric acid? Now, in order to answer that question, I'm going to need moles of nitric acid, and I'm going to need a volume of solution. And I'm given the volume. So this all comes down to finding moles of nitric acid. But the reaction is the same, only my acid is different. I have a strong acid, nitric acid, reacting with a strong base, sodium hydroxide. The protons and hydroxides react in a 1-to-1 ratio. So I'll get 1 mole of water and a mole of aqueous sodium nitrate. So yes, once again, if I want to neutralize completely so much base, I am going to need a certain amount of acid. It's 1-to-1, the ratio, stoichiometrically. And when I've been given a molarity and a volume, I've been given moles of my base. All I have to do is calculate them. I have 0.05 moles of sodium hydroxide in every liter of the solution that I'm given. And in this example problem, I'm given 30 milliliters, otherwise known as 0.0300 liters. And the volume of solution cancels. So that's how many moles of this reactant we're working with. And because it's 1-to-1, I will need an equal number of moles of nitric acid. But just to be sure, I like to write out my work. This many moles of sodium hydroxide will react with this many moles of nitric acid. Moles cancel, and I'm left with moles of nitric acid. Now, I wanted a molarity of nitric acid, and this is moles, what I want for my numerator. All I need to do is divide it by a volume of nitric acid. And there were 40 milliliters of nitric acid used. So the number of moles it took to neutralize, this many, should have been in that 40 milliliters volume of solution. And I multiply all this out and I get 0.375 molar, moles per liter, HNO3. So yes, this solution of nitric acid was less concentrated than the sodium hydroxide. That's why with a 1-to-1 ratio we needed more of it to neutralize a smaller volume of the more concentrated sodium hydroxide. So yes, we have a 0.375 molar solution here. Now, as a problem to tie all of this together and to reintroduce the concepts of limiting reagent, etc., we have this problem, namely 10 milliliters of 0.05 molar strong base are added to 30 milliliters of 0.040 molar strong acid. And the first question is, what is the limiting reagent? Well, I know that this is the reaction, strong base reacting with strong acid, ratio 1-to-1, and products are water and an ionic compound, which is aqueous, will probably still be dissolved in the solution. So yes, once again, 1 mole of this reacts with 1 mole of that. And whoever I have fewer moles of, always, would be the limiting reagent in a 1-to-1 situation. And that means the other one will be excess. It's going to be left over in the solution afterwards. So let's find who's limiting. Well, we need moles. And given a molarity and a volume, I've been given moles of sodium hydroxide. There are 0.0500 moles sodium hydroxide per liter solution. And we have 0.0100 liters of that solution, 10 milliliters. Meaning, sorry about that, 0.00050 moles sodium hydroxide. Now, to see if that's limiting, I have to compare it to moles of hydrochloric acid. And we're given that our hydrochloric acid solution is 0.00 molar HCl per liter of solution. And in the case of the acid, we have 30 milliliters of the solution, meaning we have 0.00120 moles of acid. Now we can answer the first question, who's limiting? Because we need these two in a 1-to-1 ratio stoichiometrically, but this is a much smaller number than this, which means we're going to use up all of the sodium hydroxide long before we use up all the hydrochloric acid. So answer to part A is sodium hydroxide is limiting. Then it asks how many moles of which reactant will be excess. Well, the thing left over is going to be the hydrochloric acid, some of it gets used. And to calculate excess, we always calculate what we start with, 0.0012 moles HCl, and subtract what we use. Well, without doing a fancy stoichiometric calculation, since it is 1-to-1, and I use all 0.0005 moles of sodium hydroxide, I will also use an equal amount, 0.0050 moles of my acid will be used, leaving me with 0.00070 moles of excess acid. So now I know the answer to part B. We're going to have 7 times 10 to the negative 4 moles of excess HCl. Just converting to scientific notation. 1, 2, 3, 4 times I have to move it. 7 times 10 to the negative 4. Now, what is the concentration of this excess reactant? Well, a concentration or molarity is moles per liter. So all I have to do is take this volume, or this number of moles, and divide by the volume it's in. Now be careful. What volume is the excess in? Well, let's remember we reacted these two volumes. We mixed them together to get the reaction. And this base was 10 milliliters, and the acid was 30 milliliters. So when the reaction finishes and our excess hydrochloric acid is left over, it's going to be in 40 milliliters of solution, the total amount of solution created in the reaction. So I'm going to divide by 0.04 liters, giving me a molarity of 0.0175 molar HCl. 0.0175 molar is the concentration of the excess. And now to answer the final question, what's the pH of the solution? Well, the pH is going to be determined by this excess acid. This acid is going to dissociate in 1-to-1 ratio, and we're going to have 0.0175 moles per liter of protons. So if I take the negative log of that, I'll get the pH. And the negative log is 1.04. So when the reaction is done and we're left over with some of our HCl, not all of it, our final pH is going to be 1.04.